There have historically been two avenues from number theory to get public key cryptography. The first that we've studied so far is based on discrete logarithms and cyclic groups. And the other is what's called the RSA system. The name stands for its inventors, Reverse Shamir and Edelman. And both these are in use still. And now we'll start looking at the mathematical and computational basis for this RSA system. So RSA works modulo a number n, that's hence called the modulus. And remember that when you have that, you can define the group Cn star. This is the multiplicative group of integers mod n, relatively prime to n. And that set or group has a size, its order. And remember that phi of n is that value. In the discrete log case, we often set n to a prime and worked with that. In the RSA case, it'll turn out that n is a composite. But either way, the basic mathematical fact about RSA is given by this claim over here. It's actually not new. We've seen this before when we discussed equation solving. It's just saying the same thing we did there, but I'll say it again in this context just so that we have it as the basis for RSA. So suppose we have one of these numbers and the modulus, it's some positive integer. And now I drop from n to phi of n, in the sense that given n, we know that I can compute phi of n, and it's some other integer. Once I have that integer, I can consider this set, this z star phi of n, is all the integers relatively prime to phi of n, and that itself is a group with its group operation and so forth. RSA is going to look at both the set Zn star, or this group, and this group. Here I'm picking two numbers, E and D, which belong to this group. The names stand for encryption and decryption, and they're both what are called exponents. But even in this group, they're not arbitrary. Rather, they are inverses of each other, meaning that their product, when done under this group operation, is a 1. The operation in this group being multiplication mod phi of n. Mathematically, the equation is E times D taken mod phi of n is 1. So those are our preconditions. We now know all those things are true. Now, remember that n itself defines the group Zn star. So I take some point x in that group, and I start raising it to powers. I raise it first to this power, and then the result to this power. I can certainly do that in raising to powers. I just treat these as integers, and it makes sense to raise this group element to integer powers. Since I'm working in this group, that's taken mod n. And finally, the conclusion of the claim is that when you do this operation, you just get x back. So raising to the e'th power and then taking the result to the dth power, when done in Zn star, gives you back x, assuming ED satisfy this. So we'll see this a lot. This is going to be used repeatedly, but its justification or proof is actually not terribly difficult given the math we've seen. So we know that this phi of n is the order or size of the group Cn star. And we had this nifty result saying something about computing or simplifying exponent computations. So in particular, when we take x and raise it to the ed, of course, that's the same as x raised to the power e times d. But the corollary we saw says that exponents are always taken modulo the group order. What is the group here? We're working mod n, so the group is Zn star. And so the phi of n here is the size of the group Zn star. And we can throw that mod into here for free. It doesn't actually change the result. If I don't do the mod, or if I do the mod, the this value is not going to change. But it's convenient to do it because we said here that these E and D have this property. And then, of course, the conclusion comes right out. If ED mod phi of n is 1, then this, of course, is just x to the 1 mod n, which is x. So when you walk through the math, it's quite easy to confirm this fact. But this turns out, in fact, to be quite powerful. And it also, somewhat unlike the discrete log system, has a natural interpretation in terms of encryption and decryption. So you imagine you have this number n, which we call our modulus, and we have one of these exponents. I'll call them exponents because we raise x to that power, and the E is called the encryption one, and it belongs to this set, C star phi of n. I can now define a function. The inputs to that function are in Z n star, and so are the outputs. And the function is simply exponentiation mod n, with the exponent being this E over here. So the n and the E are fixed, and the function then takes an arbitrary x from here and returns a y in that same set through this formula. Okay, I've just defined a function so far, and intuitively this function is the encryption function with x being the message. Now, suppose I have the other exponent we talked about. This is a value which is also in Z star phi of n, with the special property that it's the inverse of E in the group. So if you multiply E and D, and you take the mod phi of n, again not mod n, but phi of n, you would get back 1. I call that the decryption exponent. I can reinterpret the prior claim at a function level by saying that this function is now a permutation, and moreover, it has an inverse, and we have a formula for that inverse. The formula is to raise the input, here call it y, to the dth power mod n. So what does that amount to? What I'm saying is if I take f sub ne of x and then apply the inverse function, I expect to get back x. That's what it means, that this is the inverse of this. And if you plug in values, that's going to be true. Why? This is defined through this as x to the e. This is defined through this as raising to the d. So you get that raised to the d. And all this is mod n. And our prior claim says that x to the ed mod n is x. So that says that these two functions have reversed each other. So mathematically, the claim is not different from the prior slide, really, but it's intuitively and cryptographically closer to encryption, because now we think of this function as encrypting and this as decrypting. Okay, so RSA at first glance may seem a little complex or mysterious, so let's try it out an example. Here I'll use the number n to be 15. And so we go through the steps, and we have to look at the various sets and groups. The first one is Zn star. How do we get that? We go through the numbers 1 through 15, and we throw away anything that has a common divisor with 15. So multiples of 3 and 5 are thrown away, and here's what's left. The next step was to compute phi of n. Remember, phi of n by definition is the size of this set. So we count how many points are in there. 1, 2, 3, 4, 5, 6, 7, 8, and we get that. And now we look at the set Z star modulo this number over here. So that's Z star 8. How do we compute that? We have to look at numbers from 1 through 7 and throw away anything that has a common divisor with 8. But 8 is a power of 2, so we're throwing away just all the even numbers. So we're left with the odd numbers, and this set has size 4. Now we need encryption and decryption exponents. So at some point there may be ways to pick them, but here we can pick whatever we want subject to the conditions. So remember that the E value has to be anything in this set. So I'll decide to pick 3. But once I pick that, there's only one possible choice for the decryption exponent, which is the thing that satisfies this equation. It has to be the case that E times D is 1. And importantly, that's modulo 8, not modulo 15, but modulo 8, because all our work is in this group over here. So I use this equation to determine the decryption exponent. How do I do that? Well, once I have the equation, I probably just do trial and error. I test what are my candidates, which is everything in here, to see which one satisfies E times D is 1 mod 8. 3 times 1 is 3. 3 times 3 is 9. So 9 mod 8 is 1. So I got it already. So D will be 3. It's a little unfortunate that the D and the E values are the same, but in this example, that's how it worked out. We can now define the two functions, the forward encryption and the backward decryption. Let's call the first one F. It takes an input X, and that input X will be in this space when we've written all the possibilities here. And it cubes it mod 15. Notice here the mod is 15, not 8. We're going back to this group over here. And over here, I've tabulated results. So this is 1 cubed is 1, 2 cubed is 8, 4 cubed is what? 16 times 4, which is 64. But then you take it mod 15, and 60 is a multiple of 15, so you're left with 4, and so on. This then says, let's raise y, which is this value now, to the power of d. Coincidentally, d is also 3, so it's also cubing, but conceptually it's a different power. And here I've tabulated the results of applying that function to what's over here. And you can compute that, but what you notice is you're recovering the first column. So if you first do F and then G, you're reversing things. And intuitively, this shows that decryption truly reverses encryption. The way to succinctly think about or imagine RSA is what people call a trapdoor one-way permutation. So what do these things mean? We are interested both in the ability of the people who use it, let's say the encryptor and decryptor, to quickly perform their operations. And we're interested in something that the adversary would have a hard time doing. So if you have the modulus encryption exponent and some message input x, computing f sub ne of x is easy. Why? Because we gave a formula, it's x to the e mod n, and we studied that we have a modular exponentiation algorithm, which does that in cubic time. So this is a fast operation. If I asked you to compute the inverse function, f sub ne on some value y, and I give you modulus encryption exponent and of course y, but I also give you the decryption exponent, then this is easy. Why is that? Because we gave the formula. This is y to the power d mod n, and that's again our modular exponentiation algorithm. So we viewed this operation also as being easy. But now comes the challenge, or what we would expect or hope the adversary to be faced with. We give it the same task as here, which is to compute fne inverse of something. But in the inputs, we no longer give it this d. We just say, you don't have that. This is still well-defined given just these three things. Please try to compute it. And what we believe or expect is that this is computationally difficult. For properly chosen parameters, it's going to be rather hard in the sense of taking a lot of time to get this computation done. And we will have to see what we mean by properly or appropriately chosen parameters. And that'll be one of the next things we come to. It'll be done by an algorithm we call an RSA generator. So let's look at what that is. So far, we've seen these modulus, this RSA moduli, as something we just pluck out of thin air. But now we will be aiming to produce them via an algorithm, and with them, all the other things that we need to set up RSA. As usual with these kinds of systems, there will be some security involved, and that scales. We can be larger or smaller. And there'll be something called a security parameter, which is just an integer that determines security. The larger it is, the more secure things are. The job of the generator algorithm is to return not just the modulus, but a bunch of other things that allow us to build up an RSA system. Now, we've studied n so far as just being a general integer, but an RSA is chosen in a particular way. It's the product of two primes, and when that happens, we call it an RSA modulus. The algorithm here will actually pick those two primes. They will be distinct and odd, and output them, and then n is simply defined as their product. It will make sure that the bit length of n, remember that's what this means, is the security parameter over here. And that's where the security enters. The larger the security parameter you give, the longer or larger is the modulus. It also returns choices for the two exponents we saw, the encryption and the decryption. Both belong to the correct set. Mathematically, we're going to look at z star modulo phi of n. Once we have n here, phi of n is well defined, and E is going to belong to that set whenever the generator outputs E. So is D. Furthermore, they satisfy the property we wanted before, which is their product mod phi of n is 1, meaning D is the inverse of E in this group over here. So an RSA generator then is simply some algorithm which returns 5 things satisfying this property. But note that these properties don't uniquely define these 5 things, in the sense that there are many possible things that the generator could do, or many ways to design generators that would satisfy the conditions of outputting things satisfying these properties. And it matters how you do it, because the hardness of solving RSA will change depending on that. So we may look at that in a little bit, but before we do that, it may be worth noting another little mathematical fact which extends the one we saw before. So remember, we defined the RSA function f parameterized by a modulus and encryption exponent, taking some x and z and star, and returning f sub ne of x, which was x to the e mod n. And we said that it was a permutation on z and star. Now we're going to ask a somewhat broader question. We're going to say that you could define exactly the same function with domain Zn. In other words, why restrict the inputs to be relatively prime to n rather than just in the range from 0 through n minus 1? And our claim is that algebraically, this is actually not going to change anything, in the sense that the function will actually still be a permutation. But there's a bit of a caveat. This is true for the types of n's that we discussed right now, which are called RSA moduli and are created by generators, that are distinct, that are products of two distinct odd primes. And so that's the fact stated here. It says if n has that form, it's the product of two primes, and I have, just as before, our two exponents in z phi of n, and they satisfy E times D mod phi of n is 1, and I define f by f raising to the eth power mod n, then that function is a permutation not only on Zn star, but on all of Zn. And its inverse is given by the same formula as before. So it's a fact that in some cases will end up being useful. All right, so now in order to work better with RSA and understand its security, we're going to develop a little more math. And the first thing we're going to start with is figuring out what phi of n is. So remember that we define phi of n as the size of the group Cn star. And so far, the only way we had to figure out its value was to list the elements of Zn star and count how many there are. For example, if n was 15, we would list all numbers from 1 through 14, throw away all multiples of 3 and 5, see what was left, count up, and see that in this case there are 8. And this fact says that you can do it faster. There's actually a formula. If I know that n is the product of two primes p and q, then phi of n is given by this formula, p minus 1 times q minus 1. We don't have to go into why it's true, but you can see in this example, here if n is 15, then it's 3 times 5, and the formula says phi of 15 will be 3 minus 1 times 5 minus 1, 2 times 4, which is 8, and that does check out. So this is something we'll use, and you can also use to make RSA easier. Now we start leveraging other things that we know towards setting up an RSA and understanding its security. We said that in the RSA system, we are going to take an encryption exponent belonging to z star phi of n. And the decryption exponent is something in the same set, which is its inverse mod phi of n. It has to satisfy E times D mod phi of n equals 1. Well, we know that there is actually an algorithm which, if we give it such an E, will compute for us the decryption exponent, and that's our familiar modular inverse algorithm. It's good to note that it takes two inputs. It's not enough to just give it E. You have to tell it what group you're working in, and here that means you have to give it the value of phi of n. But if you give it these two inputs, it will in quadratic time determine the D value. And this will be useful towards setting up RSA generators. The other things we've learned, which we will again exploit, are that there are efficient ways to test primality, and we know that random numbers have a pretty good chance of being a prime. And with all that, we can at least give an example of some sort of RSA generator, just so that we know what they look like. And if you feel like implementing one, you have at least one option. So in this generator, I will actually set the encryption exponent to always be 3. That may seem a little weird that we fix it, but it turns out for security that seems usually to be fine. And efficiency goes up the smaller is E for encryption. So small exponents are often preferred. I will write the generator like this. I call it K-sub RSA because it's an RSA generator, and the superscript to indicate that E is 3. So remember, it has an associated security parameter. The larger that is, the more the security is, and that gets reflected in the bit length of the modulus n that it chooses. And remember that its job is to output 5 things: the modulus, 2 primes, an encryption exponent, and a decryption exponent. So how is it going to pick them? Well, we already saw for discrete logs that picking primes is not something for which there's a simple formula, but if you keep picking random stuff, you will eventually hit primes. So that's what we do. This time I need to pick 2 of them. I pick 2 random numbers. I pick them in this range so that their bit lengths are about half of this given k. And that's done to make sure that n, which is then defined as their product, has bit length k. Once I have the values of p and q, I'm also interested in phi of n. But now we know that there was a formula for phi of n, which is p minus 1 times q minus 1. So I compute that as well. So now I have my primes, my modulus, and the value of phi of n. But there's a bit of a caveat there. When I pick these, I don't actually know at this point that they're prime. So what I have to do is test that. I need to test those things are prime. And when I see that, I notice the other things I better ensure. I want to make sure that E falls in Z star phi of n. In other words, the greatest common divisor of E with the phi of n value has to be 1. The E I've always set to 3, so it's a question of testing that. We have fast algorithms for GCD, so no problem there. But I do need to do this test. And finally, I need to check that the bit length of n is appropriate. So what the process eventually comes down to is grab random stuff and make sure that it satisfies the properties we want. But all our stuff we studied earlier says this will work. In some reasonable amount of time, I will get these conditions to be true. What's left after that? Well, I have the n, the p, and the q, and the e. So the last thing is to get the decryption exponent, and that's the math or algorithm we just saw. By definition, it's the modular inverse of E in the group Z star phi of n, and m is phi of n. So we run that algorithm and we get D out. Okay, so we have our nice example of an RSA generator, and it's pretty canonical. So what we've done with that is we've pretty much indicated how we would set up RSA. So in other words, we can create parameters which gives us a setting where these functions f sub ne and f sub ne inverse are well defined, and we can now start thinking a little bit about security. So in RSA, the goal for the adversary is to reverse this function, and security is measured in the sense of what we call one-wayness. One-wayness means you can go forward, but you can't go backward. It's a one-way street. So the way we formulate the problem is, let's say we've chosen the modulus, encryption exponent, and an output of the RSA function. So we've run this function on some input x and obtained an output y. What we give to our adversary is the modulus and encryption exponent, so it knows what the function is, and we give it the output, but we don't give it the input. Instead, our question is exactly, please find the input for me. Everyone knows the formula for this. It's raising x to the eth power mod n, so our adversary knows that's how y is defined. And mathematically, it even knows that there is a unique x corresponding to that. But the question is, can you find that? We will assume in this case that these things are created through one of our RSA generators. So this will be a product of two primes, and this could be whatever, maybe 3. And this is created maybe based on a random value of x. So I want to look at this job from an adversarial perspective. So the way to do that is let's try. Let's take a crack at solving this problem. Before we do that, though, it may be worth formalizing it a little better, which we'll do using a game. And just like with our discrete log systems, the main difference between the game and the informal version is the game is more precise about how things are chosen. What the adversary sees and what it has to produce are the same. So first off, what is the object here whose security we're defining? For example, when we studied PRF security, it was a family of functions. What it is here is an RSA generator. Security pertains to this algorithm, the generator. I'll denote the adversary by I for inverter instead of the usual A. The game is called one-wayness, and it's parameterized by the generator. The initialize procedure runs the generator, and that'll give back this 5-tuple of objects: the modulus, the 2 primes such that n is pq, encryption exponent, decryption exponent, satisfying all the nice math properties we saw. Now our game picks a random value in Zn star, and it raises x to the eth power mod n. That computes the f sub ne function on x and gives the output y. What the adversary sees through the return statement is this challenge y, also the modulus, and also the encryption exponent. Notice that the primes and decryption exponent are never used, and they're certainly not given to the adversary. The game is simple. All the adversary has to do is just discover x. So it'll submit its guess as an output or as a call to finalize, and the game will simply check, did you find x or not? And if you do, you win, and otherwise you lose. Of course, there's some probability of winning because of all the randomization over here. And this is the probability that the game one-wayness sub RSA, when run with a particular adversary I, results in an output of true from finalize. That quantity is the advantage of our adversary. Again, the superscript tells you what the definition is, one-wayness. Subscript says we are measuring security of this generator. We can now go back to the question of saying, suppose you're an adversary and you're just playing this game. Can you win? Can you find an approach that would let you win? Well, what that means is you will get this n, e, and y as input, and you're trying to find the hidden x, the x that raised to the e at power mod n gives you y. Well, is there something you can do to approach this? How might you start? Well, there's a lot of math here, and it's pretty natural to say that I'll try to exploit that. So what's the first piece of math I might use? I actually know a formula for computing this x. Remember that RSA tells us exactly that x to the e mod n means raising y to the dth power mod n will give you back x, where d is the decryption exponent. Right? That was one of the things the generator output, and it always exists for RSA. So we look like we're making some progress here. I know that a simple modular exponentiation operation, raising y to the dth power, is going to actually work to invert RSA and recover x. At this point, I've kind of simplified things a fair bit. Okay, so why aren't we done there? Well, because if we look at our inputs, it didn't include this d. So I don't have an immediate way then of running this algorithm. However, at least it gives me some approach. It says, why don't I try to figure out what d is, and then I can do this. So I've reduced the problem of inverting RSA to one of finding d. So now I could look to see if there's more math to help me. And I know that, in fact, we had given a formula or an algorithm to compute d based on the e over here, right? Remember that d was the modular inverse of e. So the modular inverse algorithm is fast in cubic time. E is public and known from this. So if I run that, I should be able to get d, and then I should be able to take the step. So that's looking rather good. But there's a caveat. This algorithm also needs the order of the group in which you're computing this inverse. And remember that as per the math, that's phi of n, not this n, but phi of n, the order of Zn star. And now if you look here, you might notice that was also not actually explicitly provided. Of course, given n, phi of n is uniquely determined, but I would have to do some work to figure out its value. Okay, so I'm not quite there yet, but still quite a bit of progress because it says all I need to do now is compute this phi of n thing. And I don't even care now what e and y are. All I need is this, and the rest just goes back. Well, do we still have mathematical help? Well, we actually do, because we had a formula for phi of n. Remember that a couple of slides back, we said that when n is a product of two primes p and q, as we assumed here, phi of n is p minus 1 times q minus 1. So it's very easy to compute phi of n. It's just a multiplication. But again, a bit of a caveat. Where are the p and q? They're not given to you either. We know that n is equal to p times q, but they weren't given. So we come to the final link in the chain, which says, knowing that n is p times q, figure them out, and then you can invert RSA. And this is where we get a little stuck, because nobody knows how to easily figure out, given n, what are the factors p and q. So this is called the factoring problem. I give you a composite number, say a product of two primes, and I say, tell me what those prime factors are. And we will have to study that problem and look at its hardness. Now, there are some subtleties here. What we saw on the last slide is that if you can factor n, you can invert and break RSA. Conceivably, there's a way of breaking RSA that avoids factoring n. No one seems to have found one, but no one has a proof it doesn't exist. So we mostly kind of assume that the only approach is factoring. Well, towards understanding security of RSA, then, what it's come down to now is saying we are looking at a classical mathematical problem or mathematical algorithmic problem, which is just factoring composite numbers. How hard is it to do that in the sense that what is the running time of algorithms to factor? And here we'll see the same story we've seen many times repeat itself. Namely, it's quite easy to give a naive, correct, but slow algorithm. And it's the question of making it fast where you run into difficulties. In particular, how do I factor a number n, say product of two primes? Just trial division. So I try dividing it by a bunch of stuff. And any division that works, meaning it evenly divides n in the sense that the remainder of dividing n by the candidate factor is 0, then this I must be one of the two factors, and the other one is easily obtained as this ratio. So I just try candidate factors one by one. I can stop at root n since nothing bigger than that is possible as long as one exists. And I will factor. But the running time is proportional to the square root of this. And for better understanding, it may be worth writing it this way. This E is not the RSA encryption exponent, it's the base of natural log 2.7. Square root of n can be written as 2 to the E7 to the power half of the natural log of n. But since n is 2 to the power 1024 or more, this is obviously highly prohibitive for this algorithm. It turns out again, though, that there are better algorithms, and here you see their running times. And you might notice that this is the same kind of running time as the best discrete log algorithm. It's interesting that historically there was evolution. There was a faster than naive algorithm found some time back, and then there was an improved algorithm with this even better running time. Again, the formulas are a little complex. They involve raising E to powers, where those powers involve log n and then cube roots of it, or here square roots. And it takes some work to work with these and see their growth rate. But roughly speaking, their growth rate is way better than the naive algorithm, but still slow enough that for large n, these values are prohibitive. But of course, people really want to see how fast they can factor in practice. And there have been all these factoring challenges, and people have set records. The way that works is someone will publish somewhere some number n and say you win, $1,000, 10,000, 100,000 for factoring this. And then people try and they see they see how big the number has to be to make factoring difficult. And you can see the evolution. In the early 90s, people were able to factor 400-bit numbers, and that crept up. Once that used the old quadratic sieve algorithm. Once the number field sieve algorithm came in, progress was faster, and people were factoring longer and longer numbers. This was kind of a big watershed moment because industry standards and internet standards in the early 90s were 512-bit moduli. And this said, no, that doesn't work. We can factor those numbers. And then everyone had to scramble to change stuff. It's remarkable how much progress there has been after that. Not so much on the algorithmic front, but a lot of improvements in exactly how the implementations were done in the computing power available, supercomputers, parallelism, and so forth. And this started going up quite rapidly from 500 and something to 700 bits. And currently we're at 800 and something bits. So really, can factor quite large numbers. So what do you do if you want security? Well, generally speaking, our estimate is that a 1024-bit RSA modulus will take about 2 to the 80 time to factor, which is called having about 80 bits of security. That's like the smallest you can desire at present or would recommend at present. Most people would recommend higher, for example, double that or 2048 bits. And that seems fairly out of reach at present. So it's kind of the ballpark for setting up RSA securely. So towards understanding RSA, there's maybe a few more things that one can look at, especially if you happen to look around at how RSA is done in practice, look at an implementation or something. And one of those is the choice of encryption exponent. So remember, there's always this exponent. And in our example RSA generate, I set it to 3. And indeed, smaller is better because modular exponentiation is faster the smaller the exponent. And the RSA function, which is raising to the eth power and is eventually going to be encryption, thus gets faster. So people want small exponents. If you look in practice, these are some of the common values. And you could ask why. Well, the answer is that when you put these numbers in binary, they have the maximum possible number of zeros. Of course, you need a 1 at the beginning and at the end, but these numbers ensure that everything else is a 0. Why is that a good thing? It's again about speed. If you go back to our square and multiply method for doing modular exponentiation, you might, if you look at the details, notice that each iteration of the loop uses either 1 or 2 modular multiplications, depending on the value of the corresponding bit in the exponent. What that means is every time there's a 0 bit, it's half the cost of a 1 bit. So the more 0 bits, the faster things will go. Of course, you could always make things very fast by just using 3 compared to the bigger numbers, but they had some security reasons, not necessarily valid actually, to from a modern context to go to larger values. If you use RSA, you have to be careful to study and take into account different kinds of attacks that are out there. And over time, people have discovered all kinds of clever attacks. We don't have to look at them in detail, but the salient takeaway for these is that they actually all exploit small encryption exponents. However, they don't violate what we've defined to be one-way security. They kind of do other kinds of damage. And eventually what we'll do when we build things on RSA like public key encryption and signatures is rely only on this one-wayness security. And due to that, even small encryption exponents will actually be fine. If you want to see RSA at a more intuitive level, this is a nice video. It kind of does things in terms of colors and other fun stuff. So this slide is a recall of one we saw, which kind of tells you at the intuitive high level how to visualize and think about RSA and remember its properties. So remember, there's a bunch of parameters, modulus, encryption exponent, and an input. You have this function f taking all of those and returning x to the e mod n. Easy to compute, it's mod exp. So is the inverse, as long as you have the decryption exponent d. But inverting RSA, the one-wayness problem, is hard, and there you do not have the decryption exponent. Finally, something that you've probably heard about and we've neglected to say until now is all we've said about the security of number theory fails if people are able to build fast quantum computers, because there's something called Shor's algorithm, which in polynomial time can compute both discrete logs and factor. But to do that, it needs a quantum computer. And efforts to build these are underway, and people have bets as to whether it'll happen at all, and if so, when. And there's a lot of disagreement. No one seems to know. And there are sort of people pushing either side. But nonetheless, it got standardization bodies worried enough that they decided we had better already look for alternatives. And this is possible. There are alternative mathematical sources and methods to build public key crypto that don't rely on RSA and discrete log, and in particular seem, at least so far, to resist quantum attacks. And that area is called post-quantum cryptography. And some years back, relatively recently, the National Institute of Standards actually standardized such schemes for encryption.